Hello friends, today's topic of this lecture is sampling. In this lecture, we will cover the meaning of sample, need of sampling, then sampling theorem and its proof, then Nyquist rate or Nyquist interval. So first of all, before starting with the topic sampling or sampling theorem, we should know what is the meaning of sample. It can be explained with the help of an example. Like if we say that somebody is having fever or somebody is not feeling well, then what will he do? He will go to the doctor and consult the doctor. The doctor will suggest that you have to go for certain test. Then that person goes to the laboratory where the test is being executed. Then that person will give sample of his blood for testing, and after some time he will get a report which will indicate the condition of the blood present in whole body. That means instead of examining the blood present in whole body, the complete quantity of blood, what the lab technician is going to do, he will take some part of the blood, and on the basis of that sample he will conclude that this person is having fever or is suffering from some some flu or whatever. So the signal sampling is similar to this type of sampling. In signal sampling, what we are doing, say for example, if we are having a signal, it is continuous in time, signal xt, which is for example sinusoidal in nature. Then if a person wants or wish to transmit this signal which has a continuous value for its complete time period, that is from 0 to capital T. If we want to transmit this signal, then we'll have to transmit some power at each and every point or each and every value of time, because at every value of time the signal is having some amplitude. So on the other hand, if I transmit a signal which is something like this, which has samples instead of a complete signal like this, then what is difference in these two signals? In this signal we have a sample, say from 0 to this, and so on. It will be 3ts, 4ts, and so on. So in this signal, the first sample is starting from 0 and it will go down after some time. Then at a time ts, one more sample will be taken. At 2ts second, third sample will be taken, and so on. So if we will transmit this signal, then to transmit this sample, the first sample, we will need some transmitting power. So if we transmit this signal, then we will need some transmitting power. Then we have 0. To transmit 0, we need nothing. We need 0 transmitting power. Then for the next sample, again we will need some transmitting power. and then we have to transmit 0. That means we will not need any transmitting power. Then again we have to transmit a sample. We will need some transmitting power, then 0, then power, then 0, then power, then 0, and then power. So if we find average power of this signal, average transmitting power, then it is have some value, say P. Instead of transmitting this sampled signal, if I transmit this signal, the actual signal, continuous time signal, then what will happen? I will have to transmit some power at each and every point of this signal, because it has some values at every value of time, at every point. So we are not having 0. So if we will find out the average transmitting power, we will get a power P dash, and this P dash will be very, very high compared to this P. This P dash is very, very high compared to P. So the main motive, or we can say the need of sampling, is to reduce the transmitter cost. जितनी ट्रांसमिटिंग पावर आपको ज़्यादा चाहिएगी, उतनी ही ट्रांसमीटर की कॉस्ट इंक्रीज होगी. एंड एवरी सिस्टम नीड्स टू बी इकोनॉमिकली सेटल्ड. सो इकोनॉमिकली पॉइंट ऑफ व्यू से देखें तो दिस अप्रोच इज बेटर. दूसरा पॉइंट ये है कि इन टूडेज वर्ल्ड वी हैव ऑल द सिग्नल्स, और वी कैन से जो रियल टाइम के सिग्नल्स हैं, ऑल द रियल टाइम सिग्नल्स are continuous in time. Like I'm saying something, I'm speaking something, continuous in time. But all these systems, the real world systems, are discrete in time, and the reason for this is same. That is, we need less transmitting power in discrete time signal. So this is the reason that we need sampling. That is, the sampling acts like a bridge between continuous time and discrete time sampling. Then the next thing is sampling theorem. Sampling theorem is a statement which states that how the signal can be sampled and reconstructed. The sampling theorem states that a continuous time signal can be represented in its discrete form with help of samples, and the sampled signal, that is discrete time signal, can be recovered to original form when the sampling signal frequency is equal to or greater than the maximum frequency component present in the sampling signal. What does it mean? We'll come back to this statement. First of all, I let you know the mathematical form of sampling theorem. That is, Fs should be greater than or equal to twice of Fm. Here Fs is sampling frequency and Fm is the maximum frequency present in sampling signal, or the signal is which is being sampled. अब इसका मीनिंग क्या है सैम्पलिंग थ्योरम का? ये कह रहा है कि कंटिन्यूस टाइम का सिग्नल जो है, कंटिन्यूस टाइम सिग्नल, उसको हम डिस्क्रीट टाइम सिग्नल, जिसको कि हम सैम्पल्ड फॉर्म भी कहते हैं, उसमें कंप्लीटली रिप्रेजेंट किया जा सकता है विद द हेल्प ऑफ सैम्पलिंग. इट इज सेम which we have already discussed. That is, a continuous time signal can be represented in the form of a discrete time signal, that is sampled form, with the help of sampling. And this discrete time or the sampled form signal can be recovered back to the original continuous time signal if and only if the fs is greater than equal to twice of fm. सिग्नल को सैंपल करने की जो फ्रीक्वेंसी है वो उसके अंदर प्रेजेंट जो फ्रीक्वेंसी है, सिग्नल की खुद की जो फ्रीक्वेंसी है उससे ट्वाइस या फिर उससे ज्यादा होनी चाहिए. इट शुड बी ट्वाइस और ग्रेटर देन ट्वाइस ऑफ fm. So this is all about the sampling theorem. Now we come to the proof of sampling theorem. Before starting the proof of sampling theorem, we should know how to represent all this thing which you have studied. We have a continuous time signal xt and we will get a discrete time signal x of nts with the help of a sampler, and the condition is the sampler's frequency should be greater than twice of fm. This xt has a frequency fm and it should have a frequency of fs. What is nts? I'll let you know. Here ts is 1 upon fs. That is, it is called as sampling interval. This is sampling frequency. fs is sampling frequency and this ts is called as sampling interval. Now, proof of sampling theorem. We are taking an example of a signal xt, xt. We are taking just a random signal. Say this is signal xt which is to be sampled, and this signal will be sampled in the form like this. It is n, this is x of nts, and we will get the same signal envelope with the samples taken at a frequency fs. That is, if the frequency is fs, then time period will be ts. First sample is at 0, then next will be at ts, then at 2ts, 3ts, 4ts, 5ts, 6ts, and so on. Now, in this we are considering that let xt is a continuous time signal which is band limited to fm hertz. Now what does it mean? It means that if this signal is xt, then say for example, I'm not saying that we will get the same shape, but we are just assuming that let Fourier transform of this xt, that is x omega, is like this. This is minus of omega m, this is plus omega m, it is 0, and the axis is in omega. It is equal to 2 pi fm, 2 pi fm. If we take axis in frequency, it was angular frequency omega. If we take in frequency f, then these points will be minus of fm and plus fm. That means band limited to fm means the Fourier transform of given signal will not have any frequency component greater than fm. That is, it is limited to fm, band limited to fm. So band limited means what? That no frequency component greater than fm is present in its Fourier transform.